DC motor can be simply represented as a coil which is connected to a power supply and located inside a magnetic field. Now let's provide a simple model for this. First, we have a power supply shown by UM. M stands for the motor. Coil is basically a piece of wire, so it has a resistance, and because it's a coil, it also has inductance property. When the coil starts rotating in the magnetic field, some voltage will be induced in it. This voltage is referred to as generated back electromotive force, or back EMF in short. There is a current in this closed circuit called IM. The motor has also a shaft which is rotating with the angular velocity of omega m and generates a torque Tm. The shaft is also connected to a disc, or basically the load. We can also apply external torque to the disc represented by Td. This simple model has basically two parts, the electrical circuit and the mechanical part. There are two key equations that connect the electrical to the mechanical part. The first one is the generated back EMF voltage, which is directly proportional to the angular velocity. Km here is the motor torque constant. The second equation is the torque generated by the motor, which is proportional to the current. For the electrical circuit, according to Kirchhoff's law, the summation of all the voltages must be zero. So here's what we get. Let's replace UET by this equation. For the mechanical part, according to the equation of motion, we know the summation of all torques is directly proportional to the acceleration, which is the derivative of angular velocity. To intuitively understand this equation, remember a linear system. If you have a box with the mass of m, the summation of all forces must be equal to the mass multiplied by the acceleration. When we deal with rotation, force will be translated to torque. And here's the acceleration component. And finally, the mass is translated to JEQ, referred to as a rotational mass or moment of inertia. J is constant and has two parts, the rotational mass for the motor and the rotational mass for the load. To recap, here is the equation for the electrical circuit. And here's the mechanical equation of motion. As was mentioned, the torque generated by the motor is proportional to the current. So the equation becomes this. Please note that I assume there is no friction in the system. Now let's find the maximum angular velocity when the external torque is zero. For this case, the equation number 2 is simplified to this. When the angular velocity is maximum, the derivative or the slope becomes zero. So this term is equal to zero. So this means the current and its derivative are both zero. Accordingly, the equation number 1 can be simplified like this, which means angular velocity is the motor voltage divided by Km. Maximum velocity is achieved when the voltage is maximum. Now let's find the maximum current. In this case, the derivative of current must be zero as we are at the maximum point. So equation 1 can be simplified like this. And if we solve it for Im, we get this. The maximum current is reached when the second term is zero as it's subtracted from Um. This term becomes zero when the angular velocity is zero, i.e. at the very beginning or when the shaft is held stationary. So here is the maximum current. Now let's see how we can experimentally find the motor resistance. To do so, we should apply a constant voltage to the motor and hold the shaft stationary. In this case, the angular velocity is zero and the last term is gone. Also, as the voltage is constant, at the steady state, the current would be constant too, and therefore the derivative is zero. So the resistance can be easily calculated as the input voltage divided by the measured current. Given the resistance, we can run an experiment to measure Km. If we apply a constant voltage at the steady state, this term will be gone and we get this. So here's what we get if we solve it for Km. To calculate this parameter, we just need to measure the current and angular velocity. As we learned so far, the angular velocity is driven by the motor voltage and the external torque, or the disturbance. And here are two main equations describing the electrical circuit and the mechanical movement of our system. Now let's find the transfer function for the system. To do so, we need to go to the Laplace domain. Here's what we get if we apply the Laplace transform. The derivative will be replaced by s. In the first step, let's find the transfer function between angular velocity and the motor voltage when the external torque is 0. We are interested in the relation between these two, so we should get rid of Im. From the second equation, assuming the external torque is 0, the current can be expressed like this. If we replace this term in the above equation and do some simplifications, we can easily show the transfer function between angular velocity and the motor voltage becomes this. If the resistance is much higher than the inductance property, we can neglect this term, and the transfer function will be simplified to this. There are two common forms to represent this function. In the first form, we factor out Rm multiplied by J from the denominator, and therefore we get this. This is constant and we can present it as A. Also, the term in numerator is constant 2, so let's call it B. So the transfer function will be simplified to this. In the second form, we can factor out the Km squared. So here's what we get. 1 over Km is usually shown by capital K, and it's referred to as open loop steady state gain. The constant before S is also shown by tau, and it's called open loop time constant. So here is the simplified version. Now let's go back to the Laplace domain equations, and this time I'm going to find the transfer function between angular velocity and the external disturbance torque for the case when the input voltage is off and the inductance property is very small. In this scenario, these terms are gone. So the current in the Laplace domain is expressed like this. By replacing Im in the second equation, we can easily show the transfer function between angular velocity and the external torque becomes this. So to recap, the transfer function between angular velocity and the motor voltage is this. And the transfer function between angular velocity and the external disturbance torque is this. As you can see, the denominators are very similar. To make them equal, we just need to factor out Rm, and here's what we get. Now, if you compare these two, you can easily see the relation between both transfer functions. This means the overall transfer function of the system, which capture both the external torque and the motor voltage as the inputs, can be easily modeled like this. Okay, that's it for this lecture. Thanks a lot for watching, and see you in the next video.